Hello everyone. Here you can see our libraries for our Bayesian neural networks code, and what are they? Torch and torch distributions, matplotlib and numpy, of course. That's okay, and here we are starting off by defining a Bayesian linear layer. You can see, instead of using fixed weight values, this one works with distributions over the weights and bases. Basically, we are saying the weights are not a single number, they are random variables with uncertainty. This is what makes it Bayesian. Okay, now in the init method, we first set up the parameters that define the distributions for the weights. Weight mu, you will see what is that. Weight mu is the mean of the weight distribution here, and weight rho controls the variance. The values are initialized using a normal distribution. The idea behind rho is what we don't work with the variance directly. We transform rho into a positive standard deviation using the sort plus function later on. You will see that in the forward pass. That's okay, and same thing for the bias. We have got bias mu and bias rho, again sampled from normal distributions. One starts around 0, the other one starts a bit lower to keep the initial uncertainty controlled. Next up, we define the prior distributions over weights and biases. These are just standard normal distributions centered at 0. But we keep the standard deviation as a parameter, so it can be tuned, and it is called prior sigma here. That's okay, and at the end of the constructor we initialize two variables. What are they? You can see log prior and log posterior. This will help us later when we compute the KL divergence between what the model believes and what the prior says. I hope it's okay. And in the forward function, this is where things get interesting and what happens here. You will see we start by converting rho to a positive standard deviation using a soft plus transformation. So we are doing a log, 1 plus x pro, which ensures we never get negative values, and this gives us weight sigma and bias sigma. You can see here. Okay, then we sample some noise using standard normal distributions, one for weights and one for biases. These are called epsilon here, you can see. After that, we scale that noise using the standard deviation and add it to the mean. So effectively, we are deriving a sample from our current estimate of the posterior distribution. At this point, we have got sampled weights and biases for this particular forward. These are random, and if we pass the same input again, we will get a slightly different sample, which helps capture uncertainty. Then we compute the log probabilities. You can see first we evaluate the prior probability of the sampled weights and biases. That gives us log prior, right? You can see here. And next we evaluate the posterior distributions. Again, normal distributions, but now with the learned mu and transformed sigma, and calculate how likely our sampled values are under these posteriors. That gives us log posterior. And the KL divergence is going to be the difference between those two, how much the posterior deviates from prior. We solve both of those values, so we can use them during training when we compute the elbow loss, right? That's okay, I hope. And here finally we return the result of a standard linear operation using the sampled weights and biases. Okay, and let's look here. Let's take a quick look at how we actually calculate the KL divergence, and you will notice it's pretty straightforward, right? Only one line. We have already stored the logs probabilities of the posterior and the prior during the forward pass through each Bayesian linear layer. So here in the KL divergence method, we just return the difference, log posterior minus log prior. That's the KL divergence. And we will later sum these across all the layers in the network during training. Okay, let's move on to the full network. Here we are defining a Bayesian neural network class. This is basically a regular feed-forward neural network, but instead of using regular linear layers, we stack multiple Bayesian linear layers. So look at here in the constructor, we take the input dimension, output dimension, and a list of hidden layer sizes. We also pass in the prior sigma, so we can use it consistently across all layers. Then we build a list of layer sizes by chaining together input layers, and output. And let's look. Here's the main part. And what is that? We loop through the layer sizes and create a Bayesian linear layer for each pair of input and output sizes. This list of layers is stored in a module list, which is how PyTorch tracks multiple submodules in a single container. And once that's set up, we are good to go with the architecture. And I hope that's okay for you. And here forward method. What is that? This is the part that actually runs the inputs through the network. So what's happening here? You can see we are doing something called multi-color sampling, meaning instead of doing one forward pass, we do it multiple times with different sampled weights each time. And this gives us a distribution of predictions rather than a single point estimate. And we start by getting the batch size from input, and then we allocate a tensor called output that will hold all the prediction samples. And its shape is num samples, batch size, and output dimensions. That's okay. And then we do num samples forward passes through the network. In each pass, we take the input x, pass it through each Bayesian layer, and apply value after each one except the final layer. That's a common setup, no activation in the last layer, especially for regression tasks. And each result gets stored in our output tensor. Once we have gone through all the samples, we compute the total KL divergence across all layers by summing up each layer's individual KL value. That's okay, and finally we return output and the total KL divergence. So we are getting not just the predictions, but also a penalty term that we will use in the loss function during training. And look at here, predict method. This is a convenience function we use when we want to make predictions after training and also estimate uncertainty. And it is doing basically the same thing as forward, but wrapped into a no gradients block, since we don't need gradients here, right? And we call forward multiple times to get several prediction samples. Then we take the mean and variance across those samples. The mean gives us our prediction and the variance gives us a measure of uncertainty. And training parts. Look at here. There is a function called generate toy data, you will see. All it does is create some synthetic data for regression. We are generating x values from -3 to 3, then passing them through a sine function and adding some Gaussian noise. Actually pretty standard. This gives us a noisy sine wave, which is nice for testing how well our model captures both the trend and uncertainty. Then in train Bayesian NN, we start by generating 150 samples and splitting them. The first 100 go into training, the rest into test. And we create the model using one input, two hidden layers with 20 units each, and one output. We also set the prior standard deviation to 0.5, which controls the spread of the initial prior distributions. Then we initialize the optimizer, and it is add-on with a learning rate of 0.05. That's okay, and let's scroll. The training loop here, training is going to run for 1000 epochs. For each epoch, we do a few things. First, we clear the gradients with optimizer 0 grad, right? And then we forward the training data through the model using 3 Monte Carlo samples. So we are going to set 3 different outputs for the same inputs, each using different sample weights. Along with that, we also get the KL divergence term. Next, we compute the log likelihood of the predictions. We assume the output noise is Gaussian with a fixed standard deviation of 0.5. And we evaluate how likely the target values are under that distribution. And this gives us a measure of how well the model fits the training data. That's okay, and then we calculate the elbow. That's our objective function. It is the log likelihood minus the KL divergence, and here we divide the KL term by the number of training points just to normalize it by that set size. Then we take the negative of the elbow because we are minimizing. And look at here. We do usual backprop and optimizer step. Every 100 epochs we print out the loss just to monitor how things are going. And once the link is done, we evaluate the model and visualize the predictions. So now we switch the evaluation mode. We don't need gradients anymore. So we wrap things in torch, no grad again, you can see. And we create a dense grid of input points. And what are they? 200 of them between -5 and 5, and pass those through the model using 30 Monte Carlo samples. This gives us both the mean prediction and the variance at each point. For visualization, we plot the original training and test data points, and then the predicted mean as a red line. That shows us what the model has learned. And finally, we add a shaded region showing the uncertainty. That's the predicted mean plus and minus 2 standard deviations. Is drawn as a red transparent band around the mean. And this band gets wider where the model is less confident, especially in regions with fewer training points or more noise. And title, labels, legends, and call show to render the plot. Let's look our output. Here we printed the loss every 100 epochs. You can see it starts pretty high, but it steadily drops over time. By the time we hit the epoch 1000, we are down to about 198. That tells us the model is improving its fit over time. But remember, this is not just mean square error or standard loss. This is the negative elbow, which includes both the log likelihood and the KL divergence. So lower values mean the model is finding a good balance between fitting the data and not drifting too far from the prior. And move on to the plot. This shows the final predictions of the model after training. So here the blue points are the training data, and these are the inputs the model saw during training. The orange ones are the test points. So these were held out and only used for evaluation. And the red line is predicted mean of the model average over 30 Monte Carlo samples. So for each input point we run the model 30 times with different sampled weights and then took the mean of those outputs. And what is really useful here is shaded red region. That's showing the uncertainty. And it is the predicted mean plus and minus 2 standard deviations. And what we notice is this region is pretty tight around the training data, which makes sense. The model is more confident in the areas it has seen. And as we move further away from training data, especially on the far left and right, the band gets wider, right? That means the model is saying, hey, I haven't really seen much data here, so I'm not sure. And that's exactly what we want from a Bayesian model. So overall, yes, the mean prediction looks good, the uncertainty looks reasonable, and the loss has gone down over time. And all signs point to a model that's working as expected.